Hi and welcome. I'm trying to learn particle physics, today the strong nuclear force, and after we've done this we're going to do shoulder impingement training. If you participate in a shoulder impingement training, then it's very honest. The strong nuclear force. Governing theory is quantum chromodynamics. Okay, quantum chromodynamics, we were told by the weak nuclear force that we say electroweak theory, unified theory with quantum electrodynamics, the theory of electromagnetism at high energies. I have to speak it locally. Quantum chromodynamics, quantum electrodynamics. Okay, we're talking about quantum chromodynamics. But a strong nuclear force. Mediator, gluons, and they were predicted in 1962 and then discovered in 1979. Okay, the gluons are doing this quantum chromodynamic strong nuclear force, and they were predicted. There were people saying in 1962 they are gluons, and then in 1979 they were discovered they are actually gluons. And the typical range are 10 to 15 meters of a strong nuclear force. Question: when is a strong force not a strong force? Okay, we have strong force and now we want to have it is not. Answer: when it is anywhere outside the atomic nucleus. Okay, when a strong force, a strong nuclear force, is not inside of the nucleus of an atom, then it is not a strong force. Because a strong force holds together quarks, the fundamental particles that make up the protons and neutrons of the atomic nucleus, and further holds together protons and neutrons to form atomic nuclei, it is responsible for the underlying stability of matter. A strong nuclear force is only inside of the nucleus of an atom. So there's an atom with all these electrons on the shells, and then there's the nucleus in the middle, and in it are all these protons and neutrons, and inside of these protons and neutrons are these quarks. And the quarks inside of the protons and neutrons are held together by the strong nuclear force, and also the protons and neutrons inside of the atom are held together by the strong nuclear force. Its huge power is also what is released in the process of nuclear fusion in the sun, or nuclear fusion in a nuclear bomb. Okay, the strong nuclear force, which holds together the quarks in the protons and neutrons, and the protons and neutrons inside of the nuclei of an atom, is released when an atom bomb is made boom, or when the sun is doing the nuclear fusion in the sun. On subatomic scales of about 1 femtometer, and you know, a femtometer is a millionth of a millionth of a millionth of centimeter or something. 1 femtometer is a millionth of a millionth of a millimeter. So, on subatomic scales of about 1 femtometer, or 10 minus 15 meters, it is by far the strongest of the four forces. 137 times stronger than electromagnetism, and a million times stronger than the weak interaction. Gravity is so weak as to be entirely irrelevant on these scales, and that makes sense. I'm not completely able to explain why, but it makes totally sense. Now you need such a big planet just to bring 60, 70, 80, 100 kilogram force onto a human being. Such a big rock, and you have just 100 kilograms on the human being as gravity. Whereas these things so tiny and they make an atom bomb. Okay. This strong nuclear force is on that little femtometer, so a millionth of a millimeter, the strongest one of all the four forces. Stronger than electromagnetism, or the weak interaction, or even more than gravity. The fact that it is insignificant on larger scales is the paradoxical effect of an odd strong force quirk. I don't know what a quirk is, but we're saying here it is very effective in femtometer range to hold the quarks inside of the. We said it's one place where we are not able to separate the quarks. So the quarks are held together, and also the atoms are also strong together. But it is not strong on bigger range. We said it range 10 meters, so that has no power. The photon, which transmits the electromagnetic force, has no electrical charge. Okay, photons have no electrical charge, and they're transmitting the electromagnetism, that goes through the universe. These photons, I don't really understand it. Are photons light? I think light consists out of photons. Light goes through the universe. But the particles known as gluons that transmit a strong force do carry the equivalent strong force color charge. Let's do it again. The photons are transmitting the electromagnetic force. And the particle known as gluons are transmitting the strong force, and they are carrying the equivalent strong force color charge. The equivalent strong force. We do color charge was something with up quarks, down quarks, and so on. Has now the gluon themselves must have it to transmit it? As you know. They therefore participate in their own force and can interact with themselves. I don't understand it. The result is that whereas electromagnetism gets weaker when electrically charged particles are further apart, if you try and pull quarks and the gluons that bind them apart, the force between them grows stronger and brings them back together. Again. Electromagnetism gets weaker when the electrically charged particles are further apart. It makes sense. If you try and pull the quarks and the gluons that bind them apart, the force between them grows stronger and brings them back together. And that is because the gluons can interact with themselves. I don't understand it, know how to explain it, or how to understand it, but the stronger the force gets stronger, the further the quarks are pulled apart, and therefore it is impossible to pull them apart. Because the further you get them apart, the stronger you have to pull. And what if you're able to bring it over these 10 to 50 meters? Now, it seems that no one has done it before, but is it then done? Are you an over more? This phenomenon, known as asymptotic freedom, so that it gets stronger the more you pull them apart, means that strong force effects are never felt about a certain length scale. So the strong force are not felt over a certain length scale. The strong force is not acting more than 10 meters apart. But I don't understand why it should. How could it do it if the quarks are always that small together and also more or less the protons and the neutrons are that close together? I'm a bit wondering the whole time when I just said it, is it not possible to split the protons and neutrons? It also explains why neither quarks nor gluons can have a standalone existence. Yes, the quarks and the gluons cannot exist alone because they're pulling themselves so strongly together. But why do the determiner of the gluons have a color charge? Quantum chromodynamics is one of two quantum field theories, along with quantum electrodynamics, or QED, that together underlie the standard model of particle physics. Yes, there are quantum chromodynamics and quantum electrodynamics. I don't really know what I mean, but these two are there. It remains a great hope of physicists that quantum chromodynamics and quantum electrodynamics might one day themselves be united in one theory. Because it's easier to remember one or two. What is 3 times as long and difficult? The electroweak and the strong forces are thought to have acted as one in the incredible hot early first moments of the universe. Let's do it again. So the electroweak, I have to get to it one day. And the strong force. The strong force is the one with the quarks inside of the protons, which are inside of the nucleus. Have acted as one in the the electroweak and the strong force have maybe acted together as one in the incredible hot early first moments of the universe. That is interesting. That means something which does not happen at the same time or has nothing to do could have happened at that moment when no one understands basically how out of nothing has happened something. Maybe something had happened there in physics which is not existing today. Or doesn't happen today. Maybe 2 fundamental forces of the universe, which are proven to exist, but they exist only separately, have existed in that moment. Finding evidence of this grand unified theory would require recreating those highly energetic conditions. So to make that again, it would be necessary to have so much energy again, basically, as a Big Bang had, or at least a lot. What happens if a Big Bang happens if someone pulls quarks apart? I mean, no one has done this before. And just think about it, it would make sense. What if it's like a bubble gum, or like a... No, I just when you read about it, with a stronger getting force away over time, but if a strong gets forward but it would be quite nice to explain it now, but it would be like an elastic band, like a gymnastic band, but the more you put it apart, the more it pulls together. But then I thought it would be not a good idea, because it makes it very easy to understand, yes, but it gets stronger the more you put it apart, but it doesn't help to understand the whole thing. So that would be actually, I thought about it while we were talking about it, a bad idea to use that as an example. Because when the people would think, this is how it works, but they can't think on the rest gets way more complicated and it works differently. To understand that the force gets stronger when you pull it more apart, it's understandable without an example, but the example makes it complicated to understand the rest. No, but no, I want to go back to it. What if it gets stronger the more you pull it apart, and one day when you pull too much at the rubber band, it makes a big bang. Just a thought. Maybe someone should consider it if they have enough energy together to pull quarks apart. Finding evidence of this grand unified theory would require recreating those highly energetic conditions, a task currently beyond even the Large Hadron Collider, the most muscular particle smasher we have. Large Hadron Collider, they are smashing the protons together, whatever, all atoms together. But that is not enough to make another big bang, and maybe that's a good thing. So, that was particle physics. If you were here for particle physics, you go directly to the next part of particle physics. If you stay here and participate in the short and pitch project, then it's very honest. We're doing shorter circuits. We're going back with the shoulders up and front, down, back, up, front and down and backwards. Front, up, back and down. Long arms, strong fists, and go as far back as you can. High up, front, down, back, up, front, down, and again up, back, down, front, up, back, down. And now, legs wide apart, into the knees, hinge forward with a straight back as the arms sink, pinch the scapulars together. Make fists, lift the arms high up, pinch the scapulars together. Arms down, shoulders down, and pinching in the scapulars together. Make fists, lift the arms up and pinch the scapulars together. Arms down, shoulders down, and now type. Down into the knees, hinge forward, with the round back, let the arms hang, make fists, turn the arms to the inside, lift the arms up and bring them together. Straighten up, shoulders down, together. Now lift the arms high up. Bring the arms together, shoulders down and together. And release. And now time. Into the knees, hinge forward, with the round back, let the arms hang, make fists, turn the arms to the inside, lift the arms high up, bring them together. Straighten up, bring the shoulders down and together. So the shoulders high up, the arms high up, and together the shoulders down. Arms high up, and together shoulders down and together. And release. Lift the arms up, and again down. Again up. If this or any other exercise causes pain, then don't do it. Now the arms up, the shrug, and drop the shoulders up, and then go down. Again up, lift the arms up, and shoulders up, and go down. And then let's cut arms together, and bit down into the outside. And to the middle, and let's do the sundial. The arm with the sock or something at the outside, and then fall down and try to catch it again. And on the other side. And the last exercise, arm stretcher, the elephant trunk. Arm in front, shoulder back, and down. Pull the arm in, have flat fingers, try to relax the arm, go with back of the shoulder, and then the palm up to the sky. Back of the shoulder, palm of the arm. Pull the arm in, back of the shoulder, palm up to the sky, relax the arm. Pull the arm in, back of the shoulder, relax. Relax, back, pull in. Relax, and with the arm. The arm in front, shoulder back, down, Pull the arm and have fat fingers. Try to relax the arm. Go it back with the shoulder. Turn the palm up to the sky. Relax, pull in, relax, pull in. Back with the shoulder. Relax, pull in. Palm up to the sky. Relax, go back, pull in, relax. And that was the shoulder pinch training. I thank you very much and advance.